Hey guys, welcome to this session by Intellipaat. K-means clustering is an unsupervised machine learning algorithm where the aim is to group similar data points in a single cluster. And in today's session, we are going to learn comprehensively about K-means clustering. Now before we start with the session, do subscribe to our channel to get notified about our upcoming videos. And also, if you are interested in an end-to-end certification course for data science, then Intellipaat provides just the right course for you. Now let's go through the agenda for today's session. First, we will start off with a quick introduction to K-means, and then we will understand the maths behind K-means clustering. After that, we will look into the process flow of K-means. Going ahead, we will learn how to implement K-means with R. Now without much delay, let's start off with today's session.
So this is basically how the k-means algorithm works. So now what happened in the k-means is you saw that there were 4 clusters, but who decides those 4 clusters? And how can we be sure that 4 clusters are optimum? You could have even given, the algorithm could have given us 2, 3, 4, 10, or even hundreds of clusters. So what happens in k-means is we initialize some random cluster centers, or in other words, we are the people who will give in the number of clusters. So the number of clusters, let's say I want them to be 4. So it is me who tells the k-means algorithm that I want to divide this into 4 clusters. So k-means algorithm takes this input where the k value or the cluster value is 4. Now, what it does is it randomly creates 4 centers. So 1, 2, 3, 4. So these 4 centers could be anywhere. So let's say the k-means algorithm randomly selects. Okay, so we have 3. So let's say we have 4 centers. Then it randomly selects 4 centers. Now, once the k-means algorithm randomly selects 4 centers, the next step is to assign all the records which are closest to the nearest cluster center. So we have, let's say, C1, C2, C3, and C4. Now, so the record, so let's say we have record 1. So if record 1 is closest to C1, then it will be assigned to C1. If record 2 is closest to C3, then it will be assigned to C3. Similarly, if record 3 is closest to C4, then it will be assigned to C4. And this distance measure is basically the Euclidean distance. So Euclidean distance is the distance matrix which is used to calculate the distance between the data points and the cluster centers. So we have given the cluster size to be 4. After that, the k-means algorithm randomly assigned 4 centers, and then the next step would be to assign these 150 records to the center number which is closest to it. So once this is done, we will get something like this. So we have these, so consider we have one more cluster over here. So we have 4 cluster centers, and the data points have been assigned to those 4 cluster centers. Now, what happens is, since we initially gave the cluster numbers, since the k-means algorithm initially gave these centers randomly, what it does is it takes in this cluster and it finds out the mean value of this cluster, or the mean value of all of these data points, and that mean value becomes the cluster center. Similarly, for cluster number 2, it takes the mean value of all of the data points, and that mean value becomes the center. Similarly, for cluster number 3, it takes the mean of all of the data points, and that mean value becomes the center. And similarly, for the cluster number 4, it takes the mean of all of the data points, and that mean value becomes the center. So now again we have updated the center values. So again, for each of these center values, again the records, those records will be assigned to each of these updated center values. So again, the distance will be calculated. So let's see this center value, it shifted from here to here. Now again, what will happen is for each of the record, it will calculate the distance between that data point and the center. And again, similarly, those data points will be assigned to these clusters.
Just a quick info, guys. If you are interested in doing an end-to-end data science course, then Intellipaat provides you with the Data Science Architect Masters program in association with IBM. This will not only help you in mastering data science, but also gain an in-depth experience. Do check out the course details in the description mentioned below. So now let's get back to the session.
Now, this process will go on until all the records are set to each of the clusters, or in other words, no record basically moves to another cluster. So let's say for the first 3 iterations, there is this data point which was in cluster 1. In iteration 2, it went to cluster 3. In iteration 3, it went to cluster 4. But after, in the next iteration, all of the data points, they were in their same places. None of the data points moved. So this is where the k-means algorithm will stop, and this is what is known as converging of the k-means algorithm. So so this is how the k-means algorithm works, and this is how it clusters the data. Is it confusing? How much of it were you able to follow? Responses, please.
It's clear.
Everyone? So it's 70% clear, is it, Anuj? Repeat it again. Sure. Okay.
Yes.
Right.
Yeah.
So in k-means algorithm, the k, it basically stands for the number of clusters, and that number of clusters is given by the user. So let's say I want to make 3 clusters. So I'll set the k value to be 3. Now I've given the k value to the clustering algorithm, and the k-mean takes it and it randomly assigns 3 cluster points. So initially this cluster point is random. So it just places this random point anywhere. So this is a random center point, this is a random center point, and this is a random center point. And the k-means takes in only 3 center points because it is me who has told the k-means algorithm that I want only 3 center points. Now, in the next step, k-means algorithm will look at all of the data points, and it will calculate the distance of these data points from the center points. So let's see, this is my data value over here, and I will calculate the distance of this data point from this center value, this data point from this center value, and this data point from this center value. So whichever distance would be the minimum, this data point would be assigned to that cluster center. Similarly, I will take in this data point and I will check the distance between these 3 center points, and whichever distance is minimum, I will assign this data point to that particular center. Now, once this is done, we will get 3 clusters. But the problem with the initial clusters is the center points were random. So now what the k-means algorithm does is it takes the mean of all of the data points and it assigns that mean to be the center point of this clustering algorithm, of this cluster 1. Similarly, it takes the mean of all of the data points and sets that mean to be the center of this cluster 2. And again, it takes the mean of all of the data points in cluster 3 and sets that mean value to be the center point of this cluster. So again, we have updated the center values. Now, after updating the center values, we would again have to assign these data points to the nearest cluster centers. So let's say this data point was, this center was updated to over here. So in that case, again, we'll calculate the distance of this data point to the new center point, this data point to the new center point, this data point to the new center point, and wherever the distance is minimum, this data point would be allocated to that center point. And it happens again, and all of the data points are again assigned to the 3 updated center points. So again, we have 3 new clusters. Again, what we'll do is calculate the mean for each of those 3 new clusters and set those means to be the center points. Again, we'll check if any of the data points are moving or not. So if they're moving, again, this process will be repeated. So until and unless there is no data, there doesn't exist any data point which doesn't move to any other cluster, that is when we'll say that the k-means clustering algorithm is converging, and that is when the k-means algorithm will stop. So this is how the k-means algorithm works, right? So you can actually, right? So you can actually, take 1 or 2 minutes and read this flow chart. It'll help you guys out. So everyone, a quick response, please. So the math and this, is it clear? Okay, right. So now we will head on to the demo part. So yeah, you would have to load up this library of animation, which basically helps us to look at the visualization of how these clusters are forming. So I'll load up, okay, I'd have to install this package first. So let me install this package. So we'd have to wait just a couple of minutes till this package is installed. So now, after this session, what we'll do is, since you guys were asking on imputation, we'll basically look at 2 packages which are available in R for imputation. So there is one package is Miss Forest and another is HMISC. So we'll be using these 2 packages and we'll do a bit of imputation as well. And yeah, so tomorrow I wouldn't be available. So tomorrow we will not have a class. So the next class will be on next Saturday then.
Hi, while this is loading, can I ask a question? When
Sure,
we decide
sure.
like we should have 3 clusters or 4 clusters, how would you arrive at that parameter?
So again, so there is something known as a scree plot that will do it in the R coding part. So there is a way to identify the optimal number of clusters, and there is something known as an elbow method, and we'll look at that in the practical session.
Okay. And another question, sorry, I have to leave the class right now. So apart from this k-means, are we covering anything else today?
Yes, so as I said, I'll be covering the imputation since you guys had asked me to cover imputation. So again, since k-means is a small topic, so I thought I'll cover imputation as well. So again, that will take around half an hour. It's just 2 simple packages. So the video will be recorded anyway, so you can go through the recorded video.
Yeah, I'll do that. Thank you.
Yep. Right, so we have loaded up the package. Now let me use the library function.
Barney, what is that imputation, Barney? I didn't understand.
Imputation is how we can work with the missing values. So let's say if we have some missing values in data, how can we
Okay.
replace it with a missing value? Right, so someone from the
Okay.
batch had asked me to take a session on imputation. Not
It's me
sure who
only.
it
It's me
was,
only.
but okay,
It's me
yeah,
only. But the word I was known.
okay, yeah. So it'll be just a short session on imputation with just two basic packages. We'll cover that after k-means. Yeah, right.
Just a quick info, guys. If you are interested in doing an end-to-end data science course, then Intellipaat provides you with the Data Science Architect Masters program in association with IBM. This will not only help you in mastering data science, but also gain an in-depth experience. Do check out the course details in the description mentioned below. So now let's get back to the session.
So now what we'll do is we will create two sets of data points. So this runIf function basically gives us 50 values between the range of 0 and 1. So let me just print this up, right? So these are 50 values between the range of 0 and 1. And every time I use this function, I'll get a random set of 50 values between 0 and 1. So I will be storing one such set in X, the next such set in Y. Let me print X and Y over here.
Barney, one
So we
second,
have,
Barney. Why we are doing those X and Y here? Like we have, like I didn't understand what is the use of X and Y here.
so we are just creating a random data set which comprises of these two columns X and Y. That is pretty much it.
Okay, what is the use of the library of animation package then?
Animation package helps us to visualize the k-means, I mean, how the data points are being clustered.
Okay.
So we have X and Y. So with the help of cbind, I bind them into a single object and store that into data. So view of data, and this is what we have over here. So we have X values and we have Y values over here. Now, so as I had already told you, k-means algorithm basically takes in the data set and the input is the number of clusters I want to have. So I will take this data and I want to divide this data into 4 clusters. So this is the function to do that. So k-means this takes in two parameters. First is the data set, which I want to separate into clusters. Next is the cluster value, or in other words, into how many clusters I want to divide this data set. So I want to divide this data set into 4 clusters. That's pretty much it, 2 parameters, and I will store that in km. Now this k-means dot any function comes from the animation package. So again, the parameters are the same. First is the data set. Next is the number of clusters. I'll hit on enter. Let me click on plots. Let me actually stop this first and load it up again. Right. I will clear this up. So as you can see over here, there are 4 cluster centers because I have assigned the number of cluster centers to be 4, and these are being updated at each iteration. These are being updated, and also the data points are being assigned to the new cluster centers. So once once the stage reaches when no other data point goes into any other cluster, that is when this converges. So over here, this algorithm has converged, and this is how it has clustered this data set into these 4 clusters over here, right? So I had given the k value to be 4. So it randomly took 4 centers and then it kept on converging and it finally gave us these 4 clusters. Now, all of the math which we saw over there, so we can get all of that with these attributes from the KM object which we've created. So let's look at each of them. So KM dollar cluster. So this basically indicates the into which cluster the first record has been put into. So the first record has been put into fourth cluster, second record has been put into second cluster, third record has been put into second cluster, fourth record has been put into fourth cluster, right? So this is how these 50 data points have been clustered into these respective clusters. So this is how you can see which data record has been clustered, has been put into which cluster. And then you have KM dollar centers. So these are basically the mean values. So these final mean values which you see, so this center point. So if we take this as cluster 1, then for this, the mean value would be this. Again, if we take this as cluster 2, then let's say the mean value of this center point would be this. The mean value of this center point would be this, and the mean value of this center point would be this. After that, we have all of the math over here. So we have the total sum of squares. So this is basically the value before building the algorithm. It was 9.34. Now let me look at total within SS. So after we built the k-means algorithm, this 9.34 reduced to 1.95. So obviously the rest of the deviation is present in between SS. So initially it was 9.34. After we built the algorithm, it came down to 1.95. And this is the dissimilarity which is present between these four clusters. Again, this KM dollar size tells us the number of data elements belonging to each cluster. So first cluster has 11 data points, second cluster has 12, third cluster has 15, and the fourth cluster has 12. So this was a basic example where we took a random data set. Now we will perform the same operation on the iris data set. So now again, what you need to keep in mind is when you're building this k-means algorithm, it works only on numerical data. So let us have a glance at this view of iris. So this is our data set over here. Now we can apply the k-means algorithm only on numerical columns. So as we saw in this Excel file, we did all of those calculations only on the numerical values. There was no calculation with respect to the species column. So that is what we'll be doing over here. So we will apply this k-means algorithm on top of only these four columns, and we will remove out the fifth column. And let's say initially I set the number of clusters to be 3. Now let me see how this converges. So for that, I will use the k-means.any function, and I will pass in the same parameters. First is the data set. Next is the number of clusters I want to divide this data set into. And I want to divide this data set into 3 clusters. Let me delete this. Now I'll hit enter. So these 3 values are the initial assignment, initial random centers. And this is how it is converging. You see that the center points are changing, and you also see that the data points are being reassigned to the new cluster centers. So now finally this algorithm has converged, and this is what we have over here. So these are the 3 cluster centers, and this is how the 150 data points have been grouped into these 3 clusters. Now we will look at the rest of the parameters. So let's do that. KM dollar cluster. So let me have a glance at this. So we see that almost the 38, 39, 40, 41, 42, 43, 44, 45, 6, 7, 8, 9, 10. So see that the first 50 records have been clustered into cluster number 3. So this basically means that all of the Setosa species have been grouped into one cluster. Now let me zoom this. So it basically seems that these values, so these values seem to belong to the Setosa species. So all of these have been grouped into cluster number. Let's say this is 3. And the clustering for the rest of the species, which is versicolor and virginica, we see that there is a bit of mix. So a bit of virginica and versicolor is present in cluster 2. Similarly, a bit of versicolor and virginica is present in cluster number 1. So this is how, a k-means algorithm helps you to understand the similarities between different properties. And then we'll look at km dollar centers. So yes.
How do we get to know which one? I mean, in the graph, which is the cluster number 1, 2, or 3?
So you'd have to check these corresponding values over here. So let's say the sepal length is 5.9. So you'd have to check the sepal length over here. So again, since this is a 2D graph, you will get only 2 values. So we also have petal length and petal width over here. So the problem with this package or this function which we are using is, if let's say there are around 10 numerical columns, even for those 10 numerical columns, we can visualize only with respect to 2 numerical columns, right?
Just a quick info, guys. If you are interested in doing an end-to-end data science course, then Intellipaat provides you with the Data Science Architect Masters program in association with IBM. This will not only help you in mastering data science, but also gain an in-depth experience. Do check out the course details in the description mentioned below. So now let's get back to the session.
So this k-means.any, it helps you to understand visually only with respect to 2 columns. So again, if you'd have to manually check it, then you'd have to compare these values with these center points over here.
Normally, k-means, I mean, can we give for entire data set, like, or we can give individual column also for k-means while applying?
You can give it to individual numerical columns or all the numerical columns, but you cannot apply a k-means algorithm on top of a categorical column. So let's say if you want to understand distribution of the sepal length column, only the sepal length column, then maybe you initially start with 3 clusters and you want to see how those 3 clusters are there with respect to only sepal length column. So maybe some records where, let's say, sepal length is less than 4, they go into one cluster. Where sepal length is between 4 to 5, they go into one cluster, and where sepal length is greater than 5, it will go into third cluster, right? So again, that depends on your purpose. So if you want to understand with respect to all of the data, then you'll apply all of your columns. If you want to understand the clustering with respect to one particular column, then you'll feed only that column.
But
So
when we are applying entire data set, it is taking only 2 columns, right?
No, so as I said, this which you see, this is how your k-means.any shows you. But then again, it takes in all of the 4 columns. It's just that it does not show the rest of the columns. So even if there are 10 numerical columns and you're applying k-means on top of those 10 numerical columns, the visualization will be something like this when you do it with k-means.any, because there'll be one on X and one on Y, but the others you cannot see because this is a 2D graph. But then again, if you check at the attributes, then those attributes will tell you everything. So let's take this first cluster. So when you take this first cluster, you get the mean values of all the 4 columns which we've used, right? So for the first cluster, the mean value of this sepal length is just 5.9, mean value of sepal width is 2.7, petal length is 4.3, and petal width is 1.4. Similarly, for cluster 2, these are the 4 mean values. For cluster 3, these are the 4 mean values. So again, when I say mean values, these are the final values after the k-means algorithm has converged. Right? Is that clear?
Okay.
Right. So again, we have total SS. So this was before we applied the algorithm. So the 681, this is basically the same. So I had basically written down these values in the Excel sheet. So 681.3706. So this is the original value before we built the algorithm. Now k-means dollar within SS. So let's check. So 39, 23, and 15. Oh, we had actually built 4 clusters over there. Okay. So let's see. Let's actually look at the total within SS. Right. So total within SS is 78, and this was 681. So when we add up these three, we'll get 78. And the difference is stored in between SS. So when you add 602 plus 78, you'll get 681. So the lower the value of within SS, the better is the clustering. Or you can see there is greater similarity inside the clusters. And the higher the value of this between SS, you can say that the greater is the dissimilarity between the clusters. So you can check all of these attributes. And then you have km dollar size, which will tell you how many data points have gone to these clusters. Cluster 1 has 62 records, cluster 2 has 38 records, and cluster 3 has 50 records. So this is what the k-means algorithm does. But now still one question remains, which is how do we find the optimal number of clusters? So as Sanjeev had asked earlier, the optimal number of clusters, it can be found by something known as an elbow method. So let's go ahead and do that. So now I will store this only the 4 columns, the 4 numerical columns of the iris data set into my data. Let me have a glance at this view of my data. So these are our 4 columns. Now what I'll do is I will set a k-max value. So what we are doing is we will take this data set and we will iterate this through number of clusters. So first we'll divide this data set into just one cluster. After that we'll group this data set into 2 clusters, and then into 3, and then into 4. So it'll start from 1, and then we'll keep on grouping them into 20, and we'll try to understand from 1 to 20 which is the optimal number of clusters to group this data set into. So this is k-max value. So at max, I'll just say that I want 20 clusters. So I've also defined the k-max value. Now I will define 2 more variables, which is TWSS, which is total within sum of square, and the ratio. So initially this repeat function just gives me repeated values. So I am repeating this 0 k-max times. So k-max is 20. So I will just get this TWSS object where I have 20 zeros. Similarly, I'll have this ratio object which will have 20 zeros. Let me create these 2 objects, TWSS ratio. So this is pretty much it. So I've taken 2 objects and I've stored 20 zeros in both of those objects. Now I will start a for loop, and this for loop will go from 1 to 20. So for I, in 1 is to k-max. So 1 to 20, and what I'm doing is I am building a k-means algorithm 20 times. So I'm building this k-means algorithm on top of this my data and the number of centers. So in the first iteration, the number of centers or the number of clusters will be 1. And this n start which you see, so I had told you guys that initially the cluster centers are randomly assigned. So when you set the n start to be equal to 10, it will take 10 such random scenarios. So in one random scenario, there is a random assignment of clusters. In case 2, there is a random assignment of clusters. In case 3, there is a random assignment of clusters. So out of those all 10 cases, wherever you will get the maximum clustering value, we'll go with that. So this is what this n start is for. And then we have iter dot max. So this iter dot max is the number of iterations or the maximum number of iterations I want this k-means algorithm to go through. So this is a very high value. So I've given this a very high value just to make sure that our compiler doesn't tell me that the number of iterations are not enough for me to convert this k-means algorithm. But then again, normally this is actually a very high value. So for this data set which has just 150 rows, so at max it will require around 10 iterations. So I have built the k-means algorithm. After doing that, I will take this total within SS. So we know how to calculate this total within SS. So this is the total sum of squares with respect to the clusters. And I will get this total within SS for each of the clustering scenario. So when there is one cluster, I will take that and store it in TWSS1. When I'm dividing the data into two clusters, I will take this value and store it in TWSS2. When I'm dividing the data in three clusters, I will take this tot.withinSS and store that into TWSS3. Now again, I will calculate the ratio. So this is the ratio between, so this is the ratio where I am dividing the between SS upon total SS. So now we need to make sure that this value is as close to 1 as possible. So I will copy all of this and I will paste it. I'll hit enter. So any doubts with respect to this code, what we are doing? Any problem in understanding this code?
Can you re-explain any start?
So, okay, what I'll do is I'll show this. So initially, what happens is if I build a k-means algorithm, these cluster centers are defined randomly, but that will happen only once. So there is random assignment of these cluster centers, and then after that the k-means algorithm goes ahead and divides this into three optimal clusters. But when I set the n start value, then it will have multiple cases. So let me open up Paint. I'll be better explaining over there. So what I'll do is, yeah, 1, 2, 3. So this is our first scenario where these are the random assignment. 1, 2, 3. This is the random assignment. And then we have 1, 2, 3. This is the random assignment. So this n start basically gives so basically around 1 million such assignments. And out of these 1 million such assignments, I will choose that one which will give me the optimal value. Right? So this is what the n start stands for.
Okay, I got it. Thank you.
Right. What is the difference between k-mean? Okay, so k-mean just gives us all of the attributes. K-mean.any, you can visualize it. So this k-mean.any is a part of the animation package. And when you use this, you can visualize how it is clustering. K range, dataset name, criterion, tune k, $best k. Sai Kumar, so are you using the elbow method for this?
Yeah, we are using elbow method. I have referred this one from other video.
Okay.
Like this will
So
give you, this will
this
give you
will,
very easily the best k value.
okay, so this has the elbow function predefined in it, is it?
Yeah.
Okay, okay, right. So what we are basically doing is we are manually calculating the elbow value and then printing it out. But then
Yeah,
again,
I
you
got it.
also need to know. Yeah. Okay. So yeah, we have built the for loop, and now I will make the plot. So in this plot, what I'm doing is on the x-axis, I will print all of the clusters. So from 1 to 20. And on the y-axis, I will print the TWSS, which is basically total within SS. And the type of the plot is B. And then we have X lab and Y lab. So which is basically X label and Y label. I'll hit enter. Let me zoom this. So we have the total within sum of squares and we have the number of clusters over here. So this elbow plot basically tells us how the total within sum of squares is decreasing by as we go ahead and increase the number of clusters, right? So initially when we divided the data set into just one cluster, this was very high. But then again, the aim of the k-means algorithm needs to reduce this value. So when we divided this into 2 clusters, it came down to around 100 something. When we divided the data set into 3 clusters, it came down to around 90 odd something. But then again, you can't just go ahead and keep dividing this data set into these number of clusters. So that cluster value would be the optimum from where dividing will not decrease this TWSS into into a significant value. So here we see that from 1 to 2, there is a significant decrease in TWSS. Over here, there is, I mean, not as significant as this, but still there is a decrease. From here to here, it is significant enough. From here to here, it is okay. So 1, 2, 3, 4, right? So after this, we see that it doesn't change much. So from this, what you can figure out is 3, 4, 5. So maybe 4 or 5 clusters would be the optimum value for your data set, for you to divide this data set, right? So this is how you can find out the optimal number of clusters for this data set. And this is called an elbow plot, because if you look at this graph, so this is how your elbow looks when you put it on a table. So that is why it is called as an elbow plot. Right. So this is pretty much the entire concept behind k-means, the math, the theory, and this is the practical. Any doubts with this?
Like once again, could you please explain that manual one? I understood a bit, but if you better, I mean, I can understand very clear if you can explain again.
Sure. Let me zoom this. So first we took the data set.
Not the graph. I mean the code part.
This one,
Yeah.
the for loop, is it?
Yeah.
Okay. So I'll start from this. So basically the key max, when I set it to be 20, what I'm seeing is I will start dividing the data set from 1 to 20. So first I'll divide the data set into one cluster, into 2, 3, 4, and it'll go on till 20. And in this for loop, I will start from, so I'll take I, which goes on from 1 and goes till k max. So k max is basically 20. So the for loop will start at 1 and go till 20. And
What is the
this
REP will do? One second. What is the REP method will do there?
REP, okay. So let's say REP of 1, 10. So this gives me 1 10 times. So let's say 1.56. I need this 5 times. So REP repeats a value. So first parameter is the value which I want to repeat. Next parameter is the value of how many times I want to repeat this. So I want to repeat 0 20 times. Again here, I want to repeat 0 20 times. And I'm doing this because I want to store these values into this object, right? Since this for loop runs 20 times, I would have to store 20 within SS values, right? So you see this, I have 20 total within SS values, and that is why I have to initialize 20 zeros first. Is that good?
Yeah, good.
You have to mute yourself, please.
Yeah, okay.
All right. So in this for loop, this goes from 1 to 20, and I'll build this k-means algorithm. And the number of centers, it starts at 1. So initially, I'll be building one cluster, and number of start is 10. So number of start is basically the number of random initializations. So in the first initialization, the cluster centers could be assigned like this. In the second initialization, the cluster centers could be assigned like this. In the third, they could be assigned like this. In the fourth, one could be here, one could be here, and one could be at far away corner, right? So this is a total random initialization of the cluster centers. And we will do that maybe a million times. So again, this is manual, so we can set it how many times as we want. Yeah, so this is end start, yeah. And then we have iteration max. So iteration max is the maximum number of times I want this algorithm to iterate so that k-means converges. Normally, since this is a very small data set, so 150 entries is a very small data set, and it will not take more than 10 iterations to converge this data set. So let's say if you have a data set around maybe 1 lakh rows, then that is the case where you would have to need these many iterations to converge the k-means algorithm on top of the data set. So we've built the algorithm. After building the algorithm, we will take the total within SS value and store it in TWSS, which I've created over here. Similarly, I will get the ratio between SS and total SS, and I'll store it in ratio. So this is how I can manually create, manually create 20 clusters and get the TWSS values for 20 of those clusters. So once I get that, I will go ahead and build the plot. So on the x-axis, I am mapping the number of clusters. On the y-axis, I am mapping the total within sum of squares. And the label for x-axis is number of clusters, and the label for y-axis is TWSS. And the color which you see is this blue. And this is the code.
Then why you are calculating ratio there above? What is the use of the
So we are
ratio?
not using it. So I would have to manually see what is happening. So this basically tells me that this ratio value, it gets, so again, so this is 10 power minus 15, and this is so this is 10 power minus 1. So we see that this ratio value, okay, so the idea behind ratio is it needs to get to closer to 1. So the closer to 1, the better is your clustering. So we're not using this,
Yeah, here
but
it
then
is using
again,
mostly. Here we are getting everything in around 8 and 9. I think that means this model is not good, right?
where are we, what are you talking about?
I mean, you said
No, so
the
this
closer to
is,
1.
no, so this is e power minus 15. So this is basically 1 into 10 power minus 15. Right? So this is 10 power minus 15. This is 7 into 10 power minus 1. So this will be 0.7. This is 8 into 10 power minus 1. So this will be 0.8. So this is 9 into 10 power minus 1. So this will be 0.9. Right? So this is E minus 0.1. So this basically stands for 9.76 into 10 power minus 1.
Okay.
So imputation in simple terms is basically substituting the missing values. So that's pretty much what imputation is. So again, even for this, we will work with the sorry.
Barney, are you doing only the treating the missing values or you're doing scaling was there?
No, just working with the missing values. That's it.
Okay, that means like using with mean, median, and mode. That's it, right?
Yes, that will do with the HMISC package, and we'll use the Miss Forest package to impute the values with random forest algorithm. So there are other packages as well. I'll write them down. So there is mice package and there is the Amelia package. So there are like multiple packages. You can also use these two for the imputation purpose. So mice and Amelia, so the algorithm which they use is predictive mean matching. So again, we have this data set. So let's say there are some missing values. Now to impute those, so normally the easiest way to treat those missing values would be to delete all of those missing values. Even though it's the easiest, but it is not really recommended because you will lose out on some really important data. And to remove all of those records where you have missing values, all you have to do is use the any.omit function and pass in your data set, and it will remove all of the records where any values are present. After that, the next simplest would be to replace these missing values with mean, median, and mode. And then we have advanced packages. As we have Miss Forest, we have the mice package, and we have the Amelia package. So in today's class, we'll look at the Miss Forest package. So let me load this up. Library of Miss Forest, and the algorithm which Miss Forest uses is random forest, as it is very obvious with the name. So we'll be using the random forest algorithm to impute the values. And as we had seen in the previous session, so random forest algorithm is used for both numerical values as well as categorical values. Now this Miss Forest function of this package also has the prod NA. So this prod NA stands for produce NA. And with the help of this, I can introduce missing values into the original data set. So this original data set has no missing values. Now I will go ahead and introduce 30% missing values into this original data set. So this prod NA function takes in two parameters. First is the original data set. Next is the percentage of NA values that I have to introduce into the data set. So number of NA, and I'll set that to be 0.3. Now let me have a glance at this. View of iris.mis. So this is our data set with 30% missing values. So now if I look at the structure of this, so structure of iris.mis, I'll better look at the summary of this. So summary of iris.mis, and we see that sepal length column, there are 51 NA values, sepal width 44 NA values, petal length 45, petal width 40, and species 45. So when you when you compile all of this, you'll get 30% missing values in total. So we have introduced the missing values. Now this is just a one-line function. All we have to do is use the miss forest function, and so here we have introduced the missing values. Now it's time to impute those missing values. So all we have to do is use the miss forest function and pass in this data set which has the missing values. So now what it basically does is, so as we saw in the random forest algorithm, so let's say if I want to impute this value with this miss forest function, so let's say this, then this would be our dependent variable and the rest would be the independent variables. So what it'll do is it will learn from the rest of the records. So we'll take this case. So it has been predicted as 4.9 and it learns that the rest of the records have these values. Similarly, it sees that it has 4.6 and the rest of the records have these values. So the rest of the 149 records would be your training data and this would be your test data, and you would be predicting the values on this. So basically consider these 149 records to be your training data and this one record to be your test data, and your model learns on these and predicts this NA value over here. Similarly, if you're predicting this value, then again this would be a dependent variable and the rest, all of the columns would be your independent variables. Again, if you're taking this, so the rest of the 149 records would be your the training data. This would be your test data, and again if I want to predict the species, then this would be my dependent variable and the rest of the columns would be the independent variables, and all of this this function takes care of itself. So all we have to do is pass in this data frame with the missing values, and we'll store this in a new object. So this iteration is basically the number of iterations to get the final values, and you have it in iris imp. Now let me show the data set with the imputed values. Sorry, so we need to extract iris dot imp dollar. We have this x imp, so we would have to glance this dollar x imp, and this gives our data set which has the value, which basically has the imputed values. So this is our original data set with missing values. So this NA has been imputed as 4.79. Then we have this NA value which has been imputed as versicolor, but we actually know that this should be setosa, but it has been incorrectly imputed as versicolor. Right? So again, we have these three NA values, these four NA values actually over here. in record number 11, and those have been classified like this, right? So
Barney, your voice is
um,
coming a bit faster and video is a bit lagging.
okay, I'm not sure. So is it clear? Is there a lag or is it okay?
No, we can see
Others,
only this,
you can see only.
the one iris map. That's it. Only one. I can't see any other thing.
You can see only which one?
I
This data
mean,
set is. So I've
yeah,
shifted.
currently, no, it's not moving anything. Even if you try to shift it, it's not moving anything. It stuck
So
there
now,
itself.
so now I'm on the imputation tab. So do you see the imputation tab?
No,
Others? So for you as well, is it? Others, could you respond, please? So is it
We can see.
so everyone
We can see.
you can see, is it?
Yes, we
Okay.
can see.
Then Sai, it would be a problem on your end, I guess. So you could maybe check your internet connection. Right. Yep. So I was comparing these missing values with these imputed values, and this is how the imputation has been done. But then again, we see that in the process of imputation, there's a bit of error. Now, to get the error in imputation, we have this mix error function, which takes in three parameters. First parameter is the imputed data set. Second parameter is the data set with missing values. Third parameter is the original data set with no missing values. And when you give this three parameters, you will basically get two results over here. Let me check them out. So this PFC, it stands for the error in imputation when it comes to categorical values. And this NRMSC stands for error in imputation when it comes to numerical values. So in this data set, there is a 13% error in the imputation of categorical values, and there is a 21% error in the imputation of numerical values. So this is basically you can how you can find out the error in imputation. So this was the Miss Forest package. Now we also have the HMISC package. So I mean,
Barney, sorry for that. Like I missed the entire mostly what this one. Could you please go on the code? Like what is this no
sure,
NA equal to? I mean, because maybe due to my internet connection, I would have missed that. Because this
sure,
is the
I'll
one I only asked it. This what is this no NA will be doing here? 0.3.
So initially we have this data set with no missing values here with, okay. So others, is it fine if I explain from the beginning? Um, is it okay? Yeah, then I'll do that. So let me close these two tabs. So we have this original iris data set, which has no missing values, right? So this is a perfectly good data set. Now, if I want to introduce missing values into this data set, then I can use the prod any function. So prod any basically stands for produce any. And this function is a part of the Miss Forest package. So my first task is to load the Miss Forest package. Now, this Miss Forest package gives me the prod NA function, and this again takes in two parameters. First parameter is the data frame into which I want to introduce the missing values. The second parameter is the percentage of missing values I want to introduce in this data frame. So no NA or the number of NA. So basically this takes in the percentage. So I want to introduce 30% of missing values into this data frame, and I will store that result in iris.miss.
One second.
Now let me
Here is my doubt. Here is my doubt, Barney. Like why
uh,
normally anywhere, I mean, whatever the data set is there, we need to treat all
mhm.
the missing values. Why we are giving 0.3%? Like we want to treat every missing value, give some median, mode, or mean. Any out of these three only
I
we will give.
I am not treating the missing values. I am introducing missing values over here. So what I'm doing is this is my original data set, right? So there are no missing values. Let me show that. So sum of is that any iris dollar sepal length. So there are no missing values in this column. Again, let me do that for sepal width. Again, no missing values. For petal length, no missing values. Again, if we do it for petal width and species as well, there would be no missing values at all in this entire data set. Now, just for the demo purpose, what I'm doing is I am introducing 30% missing values randomly into this data set, right? So this 30% is totally random. So randomly, I am introducing 30% missing values into this data set. And to do that, I will use the prod na function. So this prod na function takes in the original data set and introduces, so again, this percentage is defined as, so if I want to introduce 100% missing values, I can even do that. So for now, what I'm doing is I am introducing 30% missing values into this data set with the help of this 0.3 value. Now, let me have a glance at this view of iris.miss. So these any values which you see, so they totally comprise of 30%, right? So basically it's 150 records into 1, 2, 3, 4, 5. So 150 into 5, you have total 750 values. So 0.3 into 750. So there'll be 225 such values where there are missing values, right? So this is what the prod na function does from all of the values. So there are 150 into 1, 2, 3, 4, 5. So there are 750 values in total. Out of those 750 values, 225 of them will be having any values. Is it clear? So we are not imputing. We are just introducing missing values.
Okay, I was confused there.
Yes. So original data set, this is our data set with missing values. Now to impute these values, so as I had said, the easiest option would be to just delete those records with the missing values. But then again, it is a very wrong thing to do because we'll be losing out on a lot of features. And to delete the values, all we have to do is na.omit and then pass in the data set, and all those records wherever any values are present, all those records would be omitted. Yeah, so that is one step which we should always avoid. Next would be to change or impute those values with mean, median, and mode. So that is another easy method. Third way would be to impute these values with machine learning algorithms. So we can so again, there are different packages which provide different machine learning functions with them so that we can impute these values. So this miss forest package comprises of the miss forest function, which imputes these missing values with the help of the random forest function. And as we already know, random forest algorithm can be used for both regression and classification purpose. And that is why we can impute both numerical values as well as categorical values with the help of this miss forest function. So how it basically works is, let's say if I want to impute this value, then these rest of the 149 records would be the training data. It learns from the rest of the 149 records and it will predict over here. So again, in this case, the sepal length would be the dependent variable and these four would be the independent variables, and the model will be random forest. So again, if I want to predict this species value over here, so this sixth record would be a test set. The rest of the 149 records would be the training set. And again, this time the dependent variable would be the species column, and the independent variables would be these 4 columns. So this is how the random forest algorithm would be implemented on top of this. And all of this is taken care by this miss forest function. So all we have to do is use this miss forest function, pass in this data frame with the missing values, and I will store that in this iris imp object. So these 5 iterations are basically the number of iterations taken to get that final imputation values. So now, if you want to look at the final data with imputed values, this iris dot, so this object which you just created, it contains this x imp attribute. So this attribute has the final data frame with imputed values. And this time I'm storing it in iris forest 1. Let me have a glance at it. View of iris forest 1. So this is the data set with missing values. This is the data set with imputed values, and the imputation has been done with random forest algorithm. So you see this NA over here, this has been imputed as 5.009. Again, these 3 NA values, it has been imputed as setosa, 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 right? So again, every time we use this, we'll get different results. So the first time when I built this, we had versicolor in one of those imputations, right? So again, we have to set a seed value. So if we use the seed value, then we'll get the same result every time, right? But then again, there'll be some cases where there is a bit of error in this imputation. And to get that error in imputation, we will be using the mix error function. And this takes in 3 parameters. First parameter is the data frame, which the final data frame with the imputed values. Second parameter is the data frame with missing values. Third parameter is the original data frame with no missing values, right? So this iris.imp$ximp is the final data set with imputed values. This is a data set with missing values, and this is our original data set. Now, let me print out iris.err, and this gives me 2 values. So this PFC is the error in imputing the categorical values, and this NRMSC is this is the error in imputing the continuous values. So this tells us that there is 4% error when we were imputing the categorical values, and there is 16% error when we are imputing the continuous values. So this is pretty much how you can work with the miss forest. So the basic algorithm behind this miss forest function is random forest, and all of these imputations are being done with the help of the random forest algorithm.
Brady, I have 2 questions. Can I ask?
Yeah, sure.
Now, in the first case itself, when you ran the algorithm miss forest, that time the errors was different. They were higher than when you ran the second time. Now, is there somewhere a method where we can optimize this also? Like, because it could be still possible that once I run it, that time the error would be high. If I run the second time, the error could be lower. Which one should I take it up?
So that again, so as we learned during model building, so that so that again, so there'll be always random values. So so every time, so let's say if we do not set a seed and we build a model, so that with respect to that model, we'll get different predictions. The second time I build a model and predict values, I'll get different predictions. So every time we do this, yes.
So I got that.
Again,
now the question is like, I got to know that in the second time when you ran it, the error was less. So ideally I should have chosen the second time rather than the first time. But if I use the seed function, then obviously I would have gone with the higher error imputation values rather than the second time when it came up as lower. So is it a process that I should run at least 3-4 times? What should I do to check it out that whether I'm using the better one or whether I'm not?
So in this case, what you can do is run this function maybe 4 or 5 times, and take values from all of those 4-5 data sets. But then again, this would be too time consuming, and but you'd have to do it. So maybe you'll get 5 data sets like these, and you would have to manually check what is the similarity between those data sets and what is the difference between those data sets. So again, that would become manual work over there, right? So with respect to this package, this is pretty much what it does. So again, so the reduction in error, you'd have to manually do it. You'd have to build it maybe 5 times, 10 times, 15 times, and compare all of those data frames and understand where the imputation is wrong, and you would maybe try to give it a right value by yourself.
Sure. Now in reality, here you had a data frame which had no missing values. Then you introduced the missing values, and then you had this comparison, and then you got an error. But in reality, I don't have an ideal data set at all. I always get a data set which has already the missing values in it. Now in that particular case, how do I get to know whether there is an error or not an error? Because I don't have anything to compare with.
Yes. So when it comes to imputation, there are actually 2 categories. One is known as missing at random. Second is known as not missing at random. So this case, what we did is missing at random, right? So these packages are basically where we are assuming that these values are missing at random. But then again, let's say we have a census data set and we are collecting. So there is one column where we are also collecting the salary of a person. Now, in that case, let's say all the high profile MLAs maybe they so let's say there are around 100 high profile MLAs, and out of those 100 high profile MLAs, 70 of them do not disclose their salaries. So in that case, there'll be 70 NA values. So for this, we would actually have to require the domain knowledge. So what we'll do is compare the rest of the 30 records. So wherever, let's say we also have the person category or the person occupation, and there's, let's say, a level such as MLA. Now, with respect to all of those 30 entries, we will compare the salary of all of those MLAs, and we will get an maybe an average value out of that. And with respect to that average value, we will try to predict the salary of the rest of the MLAs who have not disclosed their salaries. So when it comes to not missing at random cases, then we would have to require the domain knowledge. So this is for a case where this is for missing at random, right? So if there is a case where the data is not missing at random, then your domain knowledge is which plays the most important part.
The third thing, like in case of where I get a missing value, what is the maximum level where I should do an imputation, or I should just let out that parameter completely? Is there some upper limit where I can do an imputation, like 30%, 40%, 50%? If I have 50% missing values in that, I shouldn't do imputation. Is there any such rule?
So I'm not able to follow your question. So what do you mean by 50? Again, so
like for example, in a single column, I have 100 records, and in that 100 records, like for example, in sepal length, out of that 150 records which I have for sepal length, I have missing values for 100. Should I still use this parameter for my further modeling, or I should let it go? So is there some upper limit in saying how much should be imputed, how much should I not do it? Is there anything of that sort?
Not really. So this again would come down to, okay. So when it comes to real-time industry, you have an observation window and you have a performance window. So if you have included a column into your observation window, so observation window comprises of all of the independent variables. So if sepal length is there in the observation window, then it is important. But the problem is there are missing values. So now, even if there are around 70% missing values, the 10% which are there, they are contributing something which is important to the model. And that is why you have that column. So let's say out of these 150 records, there are only 15 records in this column which do not have any values. But then again, we have this column only because at least those 15 contribute something significant. So in that case, again, it comes down to domain knowledge on how you're able to impute the rest of the 135 entries of this column.
Not good. How would a domain knowledge help? Like, let's take up this iris example only. Now, if I have in the sepal length, out of that 150, I have 50 records where there is a value. Now, the remaining 100 I have to impute. What would, or I'm not able to relate, like, how could a domain knowledge help me in saying that whether I should impute and what should I impute?
So let's say if I want to impute the sepal length value. Now, again, so the sepal length is related to the sepal width. The sepal length must be somehow related to petal length, and this would also be related to petal width and species, right? So all of these columns, they are equally dependent on each other, and there is some sort of relation between them. That is why we have them in our data set. And as I had explained with respect to the Miss Forest, I mean, how it works. So let's say if I want to impute this value. Now, what it will do is this will take this as the dependent variable and these four as the independent variables. So what it'll do is it'll read this record, and it learns that if it is 3 Na 0.2 setosa, this will be a value. If it this is the case, then this will be the value. If this is the case, then this will be the value. And it internally calculates a perfect case where there's a record with no Na values here, and you get an average sort of result in sepal length, and that will be your final result. Right? Again, so as I said, omitting a record is bad, but omitting an entire column is even worse. You can't just, if you're not able to remove the, if you're not able to, remove the missing values, you can't just go ahead and remove that entire column. You'd have to find out ways by which you can impute those missing values. So again, for normally classes or for academic purposes, what we do is we go ahead and just omit that column or omit those records, because that is just the easier way to do.
Right.
But
most of the
that
times data scientist does the same thing. He omits out the records. That's the reason why I'm more keen to understand.
Not really. So that omitting would be different. So again, okay, so there are two cases. First is the case where maybe let's consider this is not our final data set. Second is the case where we'll consider this is our final data set, right? So if this is our final data set, then we would have to assume that all of these columns are equally important. But if this is not our final data set and we have to still do the data manipulation part, then we can go ahead and remove those columns which are which are not as significant as the rest of the columns. So it also depends on which part which stage of the data science life cycle you're in.
Okay. Got it. If it is at the beginning of the
Right. So let's say if you got the data set just right now, it's extremely raw.
Right.
This is not your final data set. And maybe you've got 50 columns. Out of those 50 columns, 30 of those have missing values. Then you'll try to understand out of those 30 which add significance and which do not add significance. Maybe from those 30 you will remove 15 and keep the 15. But then again, those 15 have missing values. So then you'll have to find out how can you impute those missing values in those 15 columns. So this is basically the entire process.
Okay.
Barney,
Thanks.
Barney, I have two questions, Barney, before that.
Yes.
Here where you said like we are using this for is a random forest package of that, okay, right? I mean, do we apply, I mean, that imputing the missing values for any I mean, by performing random forest model or any other model before that we can do. Suppose consider, I
Um,
don't know, suppose I consider one data set, I don't know what type of algorithm I should work on it. But there
hmm.
are missed values. Can I use directly for any model or only for random model?
I'm not able to get you. So
No,
any model or just the
I
random
mean,
forest?
let me explain clearly. Suppose now I have got one raw data set right now, just now, okay?
Hmm.
Now
Let's
in
say
the
this
data
is my
set,
data set.
yeah,
Hmm.
yeah. In this, I can see so many NA values.
Hmm.
Now I don't know what is the, I mean, to understand the data, I need to understand the clearly data, like visual, like plotting the data, and then which model will suit, like logic regression or class addition tree or linear regression or some other model. Okay. Now I need to treat those missing values
Um, but
using
then
this.
again, you will again, so machine, you will go ahead and build the machine learning algorithms only when your data is tidy. So this is
Yeah,
not a tidy data. So it
yeah,
will
yeah, yeah,
be an extremely bad idea to go ahead and build the machine learning algorithms on top of this, isn't
yeah,
it?
yeah. That's what that I understood, Barney. But I mean, before that only I should treat the missing values, right? I mean, impute the missing values.
Yes.
For
So
that, now that's what my question is. Here comes. Now actually we are using this miss forest as a random forest function, as you said. So can I
hmm.
use this package only when I apply for random forest, or can I use it for some other
No, no,
model? I
no,
mean
no, no,
algorithm
no.
also.
So it says that you are doing the imputation with the help of the random forest algorithm, right?
Okay.
You do that and then you get a data set. So you get a data set which is proper. On top of that data set, you can do anything, right?
Okay.
The
Yeah,
purpose
got
of
it.
imputation is to get a tidy data set where we have imputed this values with the least amount of error.
Yeah,
So
got
this
it, Barney. Got
has
it. Got it.
imputation has got nothing to do with the models which we build later on.
Yeah, thank you so much. Second question is,
Hmm.
uh, now we are treating the missing values, like what logic it's following, like anyway normally mostly in any method, any library, I feel like it will go with either mean, mode or median itself. Maybe the package will
Hmm.
be different, but it should follow this logic itself. Is it right?
Again, you'd have to rephrase the question.
I mean any package which we are using, or I mean by default which one, but these all will follow some logic behind that, right? I mean either
Yes.
mean one or mean, median or mode, any of these only it will follow.
No, right? So for this Miss Forest, it is using the random forest algorithm. It is not imputing the values with mean, median, or mode.
Okay. But okay.
So, right now we'll use the HMISC package. Here we'll be imputing the columns with mean, median, and mode, right? So again, there are two other packages. There is mice package and there is Amelia package. So the mice package actually imputes values with something known as predictive mean matching. And the Amelia package, it imputes values with there is aggregation approximation algorithm. So it does it with that, right? So I mean, different packages, you have different methods to impute value. And this again,
Uh,
it basically comes down to your final aims. Sometimes mean would be the ideal value, sometimes median would be the ideal value, sometimes using random forest would be the ideal value. So this
Barney,
again,
I didn't understand the. Yeah, I mean, my question. I mean, now we said it's going with the random forest. How that random forest model is treating? Any theoretical part could you explain so I can understand this one easily?
okay, so that is what I was telling you guys. So random forest, normally what we do is we have the training set, we have the testing set, the random forest algorithm learns from the training set and it predicts the values on top of the test set. You're clear till here, right? Yeah.
Yeah.
Right. And that is what happens over here. So let's say if I want to predict this value. So this record will be taken as your test set and the rest of the 149 records would be your training set. So this random forest algorithm learns from these 149 records, and it will be the value which will be predicting it would be on top of this record. And over here, the dependent variable would be sepal length, and the independent variables would be sepal width, petal width, and species. Similarly, if you want to predict this value over here, then the sixth record would be your test set. The rest of the 149 records would be your training set, and species would be your dependent variable, and these four columns would be your independent variables. So that
Yeah,
is
got it.
how this, yeah, so that
Got
is
it,
how
got it.
this function works.
Yeah, I thought like some other logic. I mean, it's indirectly implementing in inner side the random forest logic. Okay.
Yes. So what we are doing is we are imputing the values with the help of random forest.
Yeah,
That
got
is
it.
pretty
Thanks.
much what this function
Thanks.
does.
Thanks.
Right. So next we have the HMISC package. I will load this. Now again, this time I will introduce 25% missing values into the dataset. So again, this is totally random. So view of iris.mis. This needs to be capital B over here. Iris.mis, and we have introduced 25% missing values. Now, this HMISC package comprises of the impute function, and with the help of this impute function, we can actually impute individual columns of the data frame. So for each column, I can use different imputation methods. So what I'm doing is, for the first column, sepal length, I am imputing those values with mean. For second column, which is sepal width, I will impute those values with just a random value. For the third column, I'll be using median, right? So we have different methods, and we can impute the different columns with different methods. So we have that data set, and now, so this with function basically takes in one original data set, and we'll do some sort of manipulation on top of this original data set. So our original data set is this, and from this data set, I want to impute this sepal length column with the mean. So this is basically mean of this column. So these NA values which you see, those will be imputed with the mean of the sepal length column. So let's take this 8th and 10th record. We have NA values. I'll hit enter. View of iris.mis. Now let's look at 8 and 10. So you see that 5.75, 5.75. So this is basically the mean of this column. So wherever there were missing values present in this column, they were imputed with mean. Now in the second column, I will impute those values with a random number. So we have 2 and 4 over here, and I will be imputing those with a random value. So this time this is random, and I will store the result back to sepal width over here. View of iris.mis. So we have 2, we have 4. So we see that for every record wherever there was NA, we have random values. So this was imputed with 3, and this was imputed with 2.5. So this is basically a random assignment of values over here. And then for the third column, we'll be.
Could you please execute this one view of iris.mis $sepal width? Execute that command, only that one.
Yes. Iris.mis dollar sepal width, and this is what we have over here. So all of the 150.
Okay, we are storing. Okay, entirely we are storing sepal length column. Okay, we'll update it.
Yeah. I have stored this. So initially, I had imputed the sepal length column with the mean values and stored the result back to sepal length, right? I imputed these values and stored it back to sepal length. Similarly, I had imputed the values in second column and stored them back to sepal width. Now I'll do the same thing. I'll impute the values in the third column and I will store it back to the petal length column. So this time the method is median. Now let's see what are the missing values over here. So we have 6 and we have 10. Let's see what the median is. View of iris dot miss. So 6 and 10. Iris dollar petal length. Oh, this was supposed to be petal width. Sorry. So petal width. IDTH. WIDTH. Right. View of iris dot MIS. Right. So this time we have 6 and we have 10. So we see that the median value is 1.3 and it has been imputed with that median value over here. So wherever there was any, it has been imputed with the median value. So these are two such packages. So Miss Forest, the imputation is done with the random forest algorithm. HMISC provides you the impute function and you can impute every individual column with different methods. You can also check out the other packages. So yep, this is pretty much it to imputation. So normally missing it random, it is not much of an issue. So the problem comes when it is not missing it random. So that is where you'd have to do more of the manual work, understand the data set properly. To reduce the value, what do you mean by reducing the value?
Barney, how do we get to know like when we should use mean, when should we use median, and when should we use random?
That again is the what you're trying to do. Again, there is no rule of thumb for these sort of questions.
No, normally when we have outliers, we will go for median values. It always.
Again, so there are a lot of
Is that-
factors which come in. So you'd have to understand the data first, and then on the basis of the so let's say there are categorical columns. So if there is a categorical column, then mean, median, mode, those wouldn't even work, right? So if you have categorical columns, then you would obviously have to go with those algorithms which are used for classification purposes. And if it's a numerical value, then maybe you have a call to take which is the best. So sometimes let's say the data is not scattered from the mean. So all of it, so let's say there are 150 data entries and all of those data entries are closer to the mean. If that is the case, you'll take the mean value. And if there is a case where all the data entries are closer to the median, then you'll take the median value. Right? So you'd have to do all of that analysis.
Okay.
So, but for categorical values, obviously you cannot use mean, median, mode, or maybe you can't even use linear regression on top of that. You have to use some classification algorithm or some algorithm which works for both classification as well as regression.
Barney, normally which one is as per industry which packages they will use better like to treat missing values, to improve the missing values in the real time? Could you
Mice is used a lot. So mice package is used a lot because it provides different methods. So maybe you can just read up on that. Right. So what this basically does is, so as we saw with Miss Forest, we had just one case. So this mice package gives you multiple imputations. So in one imputation, we'll get certain values. In second imputation, we'll get certain values. In third imputation, we'll get certain values, right? So this mice package basically gives you multiple, multiple imputations of the same data set with missing values. and then maybe you can take an average of that, or you can find out where the problem is. So mice is one such package. So maybe you can go through this tutorial by Analytics Vidya over here.
It works for both categorical and random, right?
That depends on the method which you give. So if the method is PMM, then it is predictive mean matching, which works for categorical columns. So it basically depends on which method you're using.
Okay.
So any other questions?
Yeah. What are, I mean, could you tell like one or two more packages which I can refer for that?
Let us see. Ta-dam. So this is what we have: solution, imputation in R, which imputation is best. Well, this is what we have over here. So this gives out the same results. So mice, Amelia, Miss Forest, HMISC, MI. These are what you have. So again, mice package, it also gives you certain data sets which have pre-built missing values. So I will load this package once, library of mice. So data of So this mice package also gives you these data sets which have some missing values. So you can go ahead and work on these view of boys, right? So you already have certain missing values in these data sets. So view of brand as MA, right? So again, you have a data set. Where are the missing values? Yeah, so you have these missing values over here, right? So this data set also gives you certain data sets which already have missing values. So you can go ahead and explore all of these. Right, so is that it? Anything with respect to k-means or what we have covered with imputation, these two packages?
Normally after creating the missing values,
Uh-huh.
do we need to scaling as well for every thing? I mean, I'm not clear about scaling. Maybe I will go for the video. I just need guidance for that.
So
Like
scaling
when
depends
do we
on
use
what you do. Okay, so tell me what do you understand by scaling?
how much deviation was there? Like keeping everything constant for how much deviation from the mean, like that.
Okay, okay, let's again take this iris data set. So view of iris. Now let me actually look at the help of this. Where do we have the description? 3 species. Right. So over here it is written that again you'd have to mute yourself, please. So there's a lot of background noise. Right.
Yeah.
So this gives
Okay.
us the measurements in centimeters of the variables, right? So this is in centimeters, this is in centimeters, and these two are also in centimeters. So you'd have to scale the values where the columns or the different columns are present in different metrics, right? And again, so let's say if you're building the k-means algorithm. Now, when you're building the k-means algorithm, you have to make sure that the numerical columns which you're passing in, they are normalized. So let's say if this was in centimeters, this was in meters, this was in kilometers, and this was in maybe light years, right? So then obviously the k-means algorithm would give you extremely erroneous values. So scaling comes in where you would have to convert all of the columns into one particular case. Or what scaling does is it basically converts them without any unit. So scaling, you will subtract this with the mean and divide this with the variance. And when you do that, the unit cancels out. So these values are converted into converted between a range of values. So and those range of values basically do not have a unit. So this column will have a range of values, this column will have a range of values, this column will have a range of values, and basically there is no unit. And when there is no unit, obviously there is no distinction between these columns. So that is why you have to scale the values. So because certain algorithms, they are so for them they are very scale specific. So you have to make sure that all of the columns belong to the same scale. So that is why scaling is done.
Just a quick info, guys. If you are interested in doing an end-to-end data science course, then Intellipaat provides you with the Data Science Architect Masters program in association with IBM. This will not only help you in mastering data science, but also gain an in-depth experience. Do check out the course details in the description mentioned below. So this brings us to the end of this video. If you have any queries, please do comment below. We would love to help you. And also do subscribe to our channel so that you don't miss out on our upcoming videos.